All right, guys, last section of the year. This is chi-squared test of homogeneity. Has modern technology changed the distribution of birthdays? So before 1980, C-sections happened on any day of the week, roughly. But this Mrs. McDonald's stats class seemed to notice that after 1993, C-sections distributions changed because, as it says in the problem, why would a doctor plan a C-section on the weekend? So, to investigate, they selected, and this is important here, a random sample of people from both age categories. So this is going to be 2 random samples. And this is one of your keys, asked to tell whether this is a chi-square test of homogeneity or for independence. So this is homogeneity because it is 2 random samples. If there was just 1 random sample, it would be a test for independence. The other thing you're going to notice, well, it's not the chi-square goodness of fit because that was a list. This is going to be a matrix, okay? And if you guys have never done matrices, shame on your Algebra 2 teacher. I know that college algebra does them, but I don't think they do them in pre-calc, and I know they don't do them in calculus. So, is there convincing evidence that the distribution of birthdays has changed? Did it change from here to here? Now, obviously, they're different, but again, is it significant enough? So the first thing we're going to do is we're going to calculate the expected counts for the 2 age groups. And we're going to do it a little bit different here, okay? So to calculate what would be the expected number of C-sections on Sundays before 1980, if you look through the section, most of this you're going to do on your calculator, but to find out what the expected value is right here, you do row total times column total divided by total. I just say total, which is down there. So to find what goes in this, what the expected count is, because you observed 12, you take 21 times 77 and you divide by 150. And that equals 10.8. So observed 12 C-sections on that Sunday before 1980, and you would expect 10.8. What about, that's not right, after 1993? Row total, 21, times column total, 73, divided by total, which is 150. And that is 10.2. So what you could do then is do that for all 14 of these. Now, we're not going to do that for all 14 because the chi-square test for homogeneity and independence get a little more vast. So we're going to look at these on your graphing calculators. Now, I'm going under the assumption now that most of you have not done these, or all of you have not done these on your graphing calculators. So to do this, you're going to go under matrix, which is right here in blue. Okay? So you're going to go second matrix, and you're here. And you're only going to use this first matrix, A. So you're going to hit enter. No, you're not. Second matrix. So it's been a while. You're going to go over to edit. There you go. And you're going to put the dimensions of that matrix. Well, this has 2 rows and 7 columns. And this is for both TI-84s. I did that wrong again. Wow. 7 rows and 2 columns. There you go. That looks like our matrix back here. Okay? 7 rows. Rows go across. There are 7 days of the week, and there are 2 samples that were taken. Homogeneity, sameness. Are these 2 distributions the same? Homogeneity, sameness. Okay. There we go. 7 by 2. 7 rows, 2 columns. Sorry for that mix-up. All right. Then you're going to enter the numbers. 12, enter. 9, enter. Okay. All right, so we've entered the matrix. Now you're going to go to Stat, Test, and you're just going to select chi-square test. Your calculator doesn't know whether it's homogeneity or independence. The calculations are identical, okay? And when we get to the write-ups, you'll see that it's just a couple little wording things. Otherwise, everything is identical. So you're going to select chi-square test. Observed is A, expected is B. The calculator will calculate all of that expected for you. How nice, right? A and B, boom. 6.54 is your chi-square, which we'll get into all that. So now, check this out. You go back to second matrix. And you'll notice suddenly there is a matrix full in matrix B. And I'm going to go down to it, select it, and there are all of the expected values. So there was, I would expect 10.8 on Sunday before 1980 and 10.2. So these are all of your expected values. I think that's really cool. These are the observed, and boom, just like that, these are all of the expected. To do the chi-square test, again, you would go through individually and do observed minus expected squared over expected. You will not need to, on these big matrix chi-square tests, write out all of these values. I'm not going to have you do all 14 of those. But just so you know, you would take 12 minus 10.78 squared divided by 10.78 plus, and then go to the next one, 9 minus 10.22 squared over 10.22. Okay, and you can do all of that. What I'm telling you is when you go back, this is your chi-square value, 6.55. It does not list out all the contributions. So all 14 of those contributions are not listed out. You're not going to really ever see a question where it says, you know, what I need to see all 14 contributions. You may be asked a specific individual one, but I'm pretty sure you will not see that on the JUCO final. So don't worry about it. Those of you taking stats in college next year, worry about it. There's your p-value. So when we do the full write-up, you'll see that, hey, there is no significant difference. Okay. Degrees of freedom 6. Ooh, degrees of freedom 6. How did we get that? All right. Here's how you do degrees of freedom with these. This has 7 rows, and this has 2 columns. You do n minus 1 for both. So 7 minus 1 is 6. 2 minus 1 is 1. What is 6 times 1? 6. But it'll do that for you. It's just nice to know where they get that number. All right. So let's go ahead and finish this problem out by writing the conditions and interpreting and writing the conclusion. HO, already have it written out for you. There is no difference in the distribution of birthdays. HA, there is a difference in the distributions. Again, make sure you write the word distributions in your hypotheses. Please, please, please make sure you do that. Okay? So verify conditions. Random. Problem states. Two, and this is key why it's homogeneity. Let me say it either way. 2 random samples of people, blah, 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 were taken. Okay? One before 1980 and one after 1993. Okay? 10%. You have to do it for both. There are at least, okay, well, let's see here. We sampled 77 here and we sampled 73 here. There are at least 770 people born before 1980. I'll just do quotes because I'm running out of time. Born before, no, not before, after 1993. Normal, not normal. Large counts. All expected counts are greater than or equal to 5. Okay. And then you would write the matrix out somewhere with all of your expected counts. So you're just going to copy this second matrix down, B, enter. You'll just copy that down. Okay. Okay. So that's A. I'm not going to use table C to find the p-value. We did use the calculator. Chi-square was 6.55. P-value was 0.3645. Interpret the p-value. We haven't done that in a while. Assuming HO is true, again, you have to write this out. Write out. There is a 0.3645 probability of getting a sample difference of getting it. Yeah, this was a little tougher. Of getting a, yeah, we'll put sample difference. Sample difference, I'm running out of time, that's why I'm writing so fast. Getting a sample difference as large or larger as we did in the study. And then what conclusion would you draw? Since p-value is greater than alpha equals 0.05, fail to reject. Fail to reject. That was super sloppy. Okay.